What is the specific problem that quantized deep learning aims to solve?
The specific problem that quantized deep learning aims to solve is the demand for efficient deployment of deep neural networks on resource-constrained devices. Traditional deep learning models use high-precision representations, which consume significant computational resources and memory. Quantized deep learning techniques offer a solution by reducing the precision of network parameters and activations. This allows for more efficient deployment of deep neural networks on devices with limited resources. The goal is to maintain performance while reducing the computational and memory requirements of deep learning models, making them more accessible and practical for deployment on resource-constrained devices.
How does the straight-through estimator, SAINT, work, and why is it important in quantized deep learning?
The straight-through estimator, SAINT, works by approximating the quantization function qx with a differentiable surrogate function hat qx and using its gradient hat q, x for backpropagation. The suite is defined as hat qx equals x and hat q, x equals 1. This allows the STE to address the issue where the derivatives of quantization functions are zero or non-existent, enabling gradient updates in quantized models during training. The suite is important in quantized deep learning because it provides a simple and effective way to handle the non-differentiability of quantization functions, allowing for the training of quantized neural networks. By using the suite, practitioners can focus on other aspects of model training, such as choosing the weight initialization scheme, learning rate, and optimization method, rather than worrying about complex gradient estimators. The STE is a foundational tool in quantized deep learning, enabling efficient deployment of deep neural networks on resource-constrained devices by reducing precision while maintaining performance.
What theoretical or practical benefits are mentioned for using the STE in the proposed method?
The theoretical and practical benefits mentioned for using the straight-through estimator, SAINT, in the proposed method include the ability to simplify the training process for quantized deep learning models. The paper demonstrates that by using the suite as a gradient estimator, practitioners can focus their attention on other important aspects of training, such as choosing the weight initialization scheme, learning rate, and optimization method. The main findings show that when the learning rate is sufficiently small, applying a corresponding weight re-initialization and learning rate adjustment to a model with the suite leads to nearly the same training procedure as models with more complex gradient estimators. This simplification allows for easier implementation and understanding of the training process, reducing the need for intricate gradient estimation methods. Additionally, the paper highlights that the differences in the choices of gradient estimators, including the STE, are much less meaningful than previously thought, providing reassurance to practitioners that simpler approaches can yield comparable results in training deep neural networks with quantized parameters.
How are the main results of the paper formalized, and what are the key contributions in terms of mathematical results?
The main results of the paper are formalized through two key theorems. The first theorem focuses on the SGD update rule and states that after adjusting the learning rate and re-initializing the weights, a positive gradient estimator hat Q can be replaced by the straight-through estimator, SAINT, for non-adaptive learning rate optimizers like SGD. The second theorem pertains to the atom update rule and asserts that the suite can replace hat Q without any adjustments to the learning rate or weight initialization for adaptive optimizers like atom. The key contributions in terms of mathematical results include proving that the choice of gradient estimator has little effect on the learning process when the learning rate is sufficiently small after applying specific transformations to the weights and learning rates. These results provide a foundational understanding that practitioners can simplify their approach by focusing on basic gradient estimators like the suite and allocate attention to other aspects such as weight initialization, learning rate, and optimization methods.
What experimental results are presented in the paper, and how do they validate the main claims of the proposed method?
The experimental results presented in the paper involve comparing two modified versions of a model, one using the straight-through estimator, STE, and the other using a custom gradient estimator, HATQ. The main metrics used to validate the claims of the proposed method include compressed change point sequence agreement, quantized weight agreement, and latent weight alignment error. These metrics demonstrate that the HATQ model and the SWEET model train almost identically, with minimal impact, after applying appropriate weight initialization and learning rate adjustments. The results show that the difference between the two models diminishes as the learning rate decreases. Additionally, the experiments on both the MNIST dataset and the ImageNet dataset with ResNet 50 validate the main claims of the paper by showcasing the equivalence of training processes between models using different gradient estimators after applying the necessary adjustments outlined in the theorems. The results confirm that the choice of gradient estimator has little effect on the training process when the learning rate is sufficiently small, supporting the main findings of the paper.
What implications does the work have for practitioners and researchers in the field of quantized deep learning?
The implications of the work for practitioners in the field of quantized deep learning are as follows. For practitioners using SGD and other non-adaptive optimizers, the study suggests that by adjusting the learning rate and weight initialization of a model with a simple gradient estimator like the straight-through estimator, SAINT, they can achieve nearly the same training results as models with more complex gradient estimators. This is supported by the findings in Theorem 5. 1. For practitioners using adaptive optimizers like ADAM, the research indicates that when the learning rate is sufficiently small, they only need to consider using the SWEET or piecewise linear (PWL) estimators, as these can provide similar training outcomes. This conclusion is based on the results presented in Theorem 5. 2. For researchers in the field of quantized deep learning, this work may inspire further exploration into alternative methods for updating quantized model parameters that do not rely on gradient estimators. This could involve investigating novel approaches for computing gradients, designing optimizers specifically tailored for quantization-aware training, QAT, or exploring techniques that do not involve traditional gradient computations at all. The study also suggests that the concerns surrounding gradient error in the choice of gradient estimators may not be as significant as previously thought, encouraging researchers to focus on other aspects of model optimization and deployment. The research also addresses the question of why there are numerous published gradient estimators, despite the findings that the choice of gradient estimator may not significantly impact the training process. The study proposes that the performance improvements seen with novel gradient estimators could be attributed to other factors such as superior weight initialization and learning rate adjustments, additional contributions beyond just the gradient estimator, or the influence of quantized activation gradient estimators. Ultimately, the work provides valuable insights for both practitioners and researchers in the field of quantized deep learning, guiding them towards more efficient and effective model optimization strategies.